Did you people read the two pages that I sent from Griffiths? Now, firstly, we have solved that problem till HCV solution, Mirror solution, right? Are you people there?
Yes, sir.
Yes, sir.
Height to with the liquid level risers. We have learnt that we cannot equate the force on one side of the liquid, but we have to take the potential energy to be minimum for stable equilibrium condition. Till here we have done, yes or no?
Yes, sir.
Now listen to this. Force on a dielectric. Force on a dielectric. First of all, let me deal with this the way Griffiths has written, because he is the godfather for this. He'll write a few statements, it will be very amusing. If you people have seen the diagram, this is the diagram. Force on a dielectric, which is partly introduced. I have sent you this. Have you people seen this?
Yes, sir.
You are taking this distance to be x, right? This will be L minus x. You're pulling with a force F. You're pulling this dielectric outside. You're pulling it up. Right? Now, we are interested to know what is the force on the dielectric. Why should there be force on the dielectric here? Why should there be force on this particular dielectric? Field is always perpendicular. Listen to the language Griffiths uses. We have always pretended that the field is uniform inside a parallel plate capacitor and zero outside. We have always
Pretend.
pretended that the field is uniform inside the parallel plate capacitor and zero outside. Technically, this will be the field. If you see the positive charge here, if you see the positive charge here this way, sharper the edge, greater the charge density. Right? Now, this fringing fields are something that we have been neglecting all through. If this were literally true, if what were literally true, that the field is uniform inside and zero outside, if it were literally true, there would be no net force on the dielectric at all. There would be no net force on the dielectric because field is perpendicular. However, there is in reality a fringing field around the edges. These are called fringing fields. Sharper the edge, greater the charge density. So these are the fringing fields around the edges, which for most purposes can be ignored, which we have been doing till now. We have been ignoring the fringing field. But in this case, it is responsible for the whole effect. Right? It is this non-uniform fringing field that pulls the dielectric into the capacitor. It is this non-uniform fringing field which pulls you will have induced charges this way, positive charge, negative charge. You have induced negative and positive charges. Because of the fringing fields, there will be forces this way. The vertical components cancel out and horizontal components add. Right? It is this non-uniform fringing fields that pulls the dielectric into the capacitor. Fringing fields are notoriously difficult to be calculated. Listen to the language. Fringing fields are notoriously difficult to be calculated. Luckily, we can avoid this altogether by the following ingenious method. By the following
Ingenious method.
he is the godfather for this concept. That's why you don't find this in Halliday Resnick. That's why you don't find this in university physics. He is the godfather for this concept. And he'll make you feel all throughout this derivation that he is the godfather for this concept. Listen carefully. Let W be the energy of the system. It depends, of course, on the amount of overlap. If I pull the dielectric out by an infinitesimal distance dx, he will write F me. If I pull the dielectric, he makes the student feel at every point that he is the godfather for this concept. F me, he says. Generally, when we say somebody pulling, we write F external. He writes F me. If I pull the dielectric out by an infinitesimal distance dx, the energy is changed by an amount equal to the work done. dW is equal to force exerted by Griffiths into dx.
So no heat loss.
Pardon?
No heat loss.
What is it connected to?
Nothing.
Right? Second, even if there is electromagnetic heat loss, you are moving it only by distance dx. Dx is very, very small. So this will technically be du. This will be force exerted by Griffiths into dx into cos 0. This will be minus F. What is the force exerted by Griffiths? Equal to the force acting inside, because whole of the energy you are taking into potential energy. That means no change in kinetic energy. No change in kinetic energy means the force exerted by Griffiths should be equal to this force. Agreed? F is equal to minus du by dx, something that we had known. We would have used this directly, but then Griffiths did it this way. So I am presenting it the way he did it. Now, this is the force acting on this dielectric minus du by dx. Fine. Now, then he calculates in this particular case. In this particular case, he is calculating C. Can I claim C1 and C2 are in parallel?
Yes, no.
Now, even before that, let me tell you the general expression for this. F is du by dx. U is equal to q square by 2c. F is equal to minus du by dx. This is minus q square by 2, 1 by c square into dc by dx. Q square by c square half into dc by dx. This will be the force exerted, and he goes one step ahead. He writes this as half v square dc by dx. You can write q by c as v. You can write q by c as v, yes or no?
Yes, sir.
But if I were given a choice, I will not. There is a reason for it. Here, battery is not connected, so potential is not constant, but charge is constant. Charge is constant. So I would prefer to leave the formula here than to write it as v square. Right? Because potential is not constant. Potential is a variable. Q is constant. So I would prefer to leave the formula here for reasons that you will understand. Right? Now
Yes.
look at this. C will be C1 plus C2. I want dC by dx. So this is C1 and C2. C1 epsilon naught B into this distance is x divided by d. Epsilon naught B, this is C1. C2 is epsilon r, epsilon naught B into L minus x divided by d. See if you are convinced by C.
So what is it? X equal to dx.
Yeah,
So he had moved it by very small distance, right?
I didn't get you.
So Griffiths had moved it by a distance of dx, right?
तो पहले C calculate करने दो तभी तो dC by dx आएगा. C at this instant, this is C1, this is C2.
Sorry, Xander.
C1 is this, epsilon naught bx by d, right? This is C2, epsilon r, epsilon naught, area is L minus x into b divided by d.
Yes.
C1 and C2 are in parallel, agreed? Now dC by dx will be epsilon naught b by d plus epsilon r, epsilon naught b into minus 1 by d. This will turn out to be 1 minus epsilon r, epsilon naught b by d, dC by dx. Now, problem with foreign author is they don't do spoon feeding. He writes the negative sign. They don't do all this simplification. Directly they write this. The negative sign tells me that the force is inverse. Now in this equation, we keep scratching our head. Why should there be negative sign? Later on, when we see dC by dx turns out to be negative, epsilon r is a number greater than 1. Right? dC by dx, when you substitute here, you will get the force to be negative. Force was positive, x would be increasing. Force is negative, implies it will be in the direction of decreasing x. Decreasing x means the force will be inverse, which you have taken is correct. Right? Substituting this dC by dx here, and he writes the negative sign tells us that the force is acting inwards. This is the first step of this particular derivation. Rather, this is the way he did it. I have something missing here. I may, right? Fine. So this is the first part of it. You found out C1, C2, dC by dx and substitute here. Now watch out for this. I am running short of space here. You will substitute dC by dx here with q square by c square, and that will be the expression. More appropriately, I will substitute it in this equation, not in this equation. Why? Because v is not constant. Q is constant in this case. Technically, you did not calculate the force directly. You calculated the potential energy and you differentiated the potential energy. First, to take this down till here, I'll speak about the second half of the derivation, which Griffiths actually skipped. He gave it in one line, but we'll do it in detail.
Excuse me, sir.
Hmm.
So I had a doubt from one sentence in the passage that Griffiths wrote.
Hmm.
You just went through it. So the field could not terminate abruptly at the edge of the capacitor, for if it did, the line integral of E around the closed loop would not be zero. Sir, I didn't understand the meaning of this.
Temporarily, don't worry about that. That comes with the divergence and curve, which we didn't explain. So I left that line.
Right, sir.
Noted, sir.
Now, Griffiths writes one particular point which quite a few authors commit as a mistake, though they have picked it up from him itself. He writes one point. If you people have read that line, it is a common error to use this equation. F is equal to minus d by dx of half cv square minus half v square dc by dx. It's a common error. To use this equation when the battery is connected. One then obtains F is equal to minus half V square dC by dx, which is off by a sign. Off by a sign. Which is off by a sign. It is of course possible to maintain the capacitor as a fixed potential by connecting it to a battery. But what is this problem? But in that case, why is this wrong? He says the negative sign dC by dx is negative, this is negative. Negative of negative becomes positive. Then the force will be outwards, which he says is wrong. Then where are we going wrong? Now battery also does work. Now this expression itself is wrong. Now he says you will have to write work done by me, work done by Griffiths, plus work done by battery should be equal to du. Now he writes this as force exerted by Griffiths dot dx plus b dq is equal to d. F me is equal to minus f dx. F me and f are in opposite direction. V d of cv is equal to du minus f dx plus v square dc is half v square dc by dx. U is substituted as half cv square. Now f dx is equal to v square dc minus half v square dc. I am bringing this dx to the denominator here itself. So I will not have dx here. This will be dc by dx. This will be dc by dx. This is half v square dc by dx. Something that he expects. If you people have observed, this dx I brought it to the denominator. Right? du is d of half c v square. I brought dx to the denominator. Du by dx, and hence I get this. Till here, are you clear?
Yes, sir.
Are you able to explain the difference in the negative sign? Here, this will be wrong because you are taking only work done by Griffiths. Here, you are taking even work done by the battery. Now, substitute dc by dx, half v square. How much did you get dc by dx? Do you remember? Turn the page and tell me.
So 1 minus epsilon naught r multiplied by epsilon naught into b by d. Epsilon naught into b by d.
Now 1 minus epsilon r will be giving me the negative sign. That tells me that the force is inverse. So right now I'm taking the force inverse and I'm writing it as epsilon r minus 1. Epsilon naught b square by 2b into epsilon r minus 1. This is the force when the battery is connected. Two things that you'll have to remember. First point. When the battery is connected, you cannot use the previous case directly and just ignore the negative sign. No. You'll have to take work done by the battery as well, and you will get this force. When the battery is not connected, dc by dx, you already know half q square by c square dc by dx. Or half v square dc by dx. Here, potential is constant. Previous case, potential was not constant. Something very important here. Why did you explain this after dealing with the controversial Irdov's problem? In Irdov's problem, they asked you, what is the height to which the liquid rises? All the forces you knew actually summed up to be zero. All the forces you knew actually summed up to be zero. So what was the force which was pulling the dielectric above, liquid dielectric? Have a look. This was the positive charge. This was the negative charge. If you add a liquid, the liquid dielectric will move up. Right? This will move up. What was the force which was pulling the dielectric above? Now see, these fringing fields here will pull any dielectric inwards. Now when they pulled the liquid inwards, the liquid level will rise. These fringing fields will pull any dielectric inwards. When they are pulling this liquid inwards, the liquid level will rise. Right?
Yes, sir.
So which was the force which was pulling the liquid above? The force due to the fringing fields?
Yes, sir.
Which was the force which was pulling the liquid above? The force due to the fringing fields? Right?
Yes.
Now this force, Griffiths writes, is notoriously difficult to be calculated, but for my ingenious method of potential energy. What did he use? Rate of change of potential energy. How did we calculate the previous problem for stable equilibrium? We calculated the potential energy into minimum potential energy.
Yes, sir.
Now you understand the sink in the two. So what is the force which is pulling this liquid dielectric above? It is the fringing fields. Why could you not directly calculate from the force? They are notoriously difficult to be calculated. What procedure do you want us to use? du by dx. And hence you will get the height to which the liquid level rises. Now you understand why Irdov changed his answer in the second and the third edition. Very first edition, Irdov's answer was the same as the one given by HCV. In fact, HCV followed the first edition of Irdov. Right? Later editions, Irdov made the change. This is the reason why he made the changes. Right? Now here there will be one more small doubt that will come to your mind after a certain time. Griffiths writes a statement which is not very genuine here. He writes, the force on the dielectric cannot possibly depend on whether you hold the charge constant or potential constant. Either way, he tells you are getting the same expression, half v square dc by dx. He tells you, you're able to see this part of the board.
Yes,
Either way, he says, whether you are holding the charge constant or the potential constant, you are getting half v square dc by dx. Right?
Yes, sir.
yes,
Technically, the statement is not 100% correct. Why? When I am keeping the potential constant, this V is a constant. But when I am keeping the charge constant, this V is a variable. You cannot tell me both are the same. What he meant is the format of the expression is the same. You cannot tell me both the expressions are the same. Right? In fact, he emphasizes and he writes, please understand the force on the dielectric cannot possibly depend on whether you plan to hold the charge constant or potential constant. Though the expressions format will be the same, half V square dC by dx, value of V changes. Here, when you connect it to a battery, V is a constant. When you did not connect to a battery, V is a variable. Q remains constant as C is changing. So Q by C will be a variable. So very technically, the statement is not 100% apt. What he meant was slightly different when compared to what he wrote. Now, listen to the next para, the last para. After some days, you will get this doubt. This potential energy expression which you calculated as half CV squared, you calculated from uniform field. Listen
Yes,
carefully.
sir.
This half CV square you calculated from where?
Infinite.
From uniform field inside the capacitor.
Yes.
Right? Now, force is due to fringing field and not due to the uniform field. Force is due to the fringing field, not due to the uniform field. You are taking a rate of change of the uniform field and you are telling me that is the force. But the root cause for the force is fringing field. Do you get the doubt?
Yes, sir.
Fringing field to liya hi nahi aapne. Energy you calculated from the uniform field. Rate of change of that energy you are telling me the force due to the fringing field. Listen. Energy stored in the fringing fields themselves stay constant. Last line of that page. Energy stored in the fringing fields themselves. In the bracket he writes, which was not accounted for in the derivation. In the bracket he writes, which was not accounted for in the derivation. In the derivation you didn't take the energy of the fringing field. Why? Because even if you put that, it is constant. On differentiation of that constant, it turns out to be
0.
Right? As the slab moves, what does change is the energy well inside the capacitor, where the field is nice and uniform. As the slab moves, what does change is energy well inside the capacitor, where the field is nice and uniform. The last line of that particular page. Right? If you people have that with you, it is very beautifully presented, and quite a few times you will get this doubt after a few days when you go through it. Potential energy, you took the uniform field. Fringing field is the root cause for force. You are differentiating this potential energy because the energy stored in the fringing field is constant. When you put that in the differential, differentiation of constant will become 6. What changes when the dielectric is moving? Now, it may look absurd. Fringing field is the root cause for the dielectric to move. But energy changes in the uniform field. Listen carefully. Fringing field is the root cause for the dielectric to move, but energy change is happening in
Uniform.
uniform field, not the fringing field. ऐसा भी हो सकता है क्या? बहुत बार हुआ ना यार. Friction is the root cause for my walking, but energy loss is happening in my internal energy. Friction, work done by friction is 0. Without friction, I cannot walk. But energy loss कहाँ पर हो रहा है? Internal energy से हो रहा है. Number of calories burned. Physics में how many number of times we came across this, and we will keep coming across. Root cause or the force due to for a particular body to move is something else. Work is done by something else. When you walk, work done by friction is 0, but internal energy is doing work. For the dielectric to move, fringing field is the root cause. But energy change कहाँ पर हो रहा है? Uniform field में हो रहा है. Physics behaves this way in many situations. Root cause for it to happen. I'm climbing steps. Work done by normal force is 0. Internal energy does work. Root cause for my climbing steps is normal force. But internal energy is used up. Root cause for the dielectric to move inside is the fringing field. But energy difference is happening in the uniform field inside. That's the beauty in it. Make a note of that statement after you come till here. I'll dictate that statement.
Excuse me, sir. So just a doubt. So there you flipped the sign on force, right, at the last step. So why did you do that? One instead of 1 minus epsilon or r, you took
I
epsilon r
wrote the
minus.
magnitude. I just wrote the magnitude.
Right, sir.
Sir, I have a doubt.
Hmm.
Sir, how did we come to know that fringing field's energy is constant?
That actually is proved in more than one way. For that, you'll have to go to the 4th, 5th page of this derivation. Right? He will show that the fringing field's energy will be constant. He does it in a very self-explanatory way, this textbook. Everywhere where there is a question, he answers it and he proves it. For that, again, this curl, in that para, if you people see, he again referred to del cross E equal to 0. Now, this del cross E is not yet defined for you. So skip it, but remember.
Sir, I had a doubt about the previous derivation. You hadn't considered work done by the battery, so how did you end up getting the right answer anyway?
Here,
Oh no, sir, in the previous derivation, the one that you
previous
erased.
battery है ही नहीं, ढंग से देख लो. Battery है ही नहीं.
Right, right, sir.
Hence, we didn't consider the work done by the battery.
सर
Hmm.
सर फ्रिंजिंग फील्ड में क्यों पोटेंशियल एनर्जी चेंज नहीं होगा?
हाँ, fringing field में potential energy remains constant.
सर वो चेंज क्यों नहीं हुआ?
You are sleeping till now. अभी 2 मिनट पहले एक बच्चे ने पूछा and I have answered it. Again, you repeat the same question. The derivation of that is given after 3 pages in Griffiths. You'll have to wait till curl is stopped.
Oh, okay.
Can I dictate that note?
Just a second, sir.
Yes, sir.
Also, so I'm having trouble visualizing in which direction the field is exerting the force on the dielectric. So because here I can see it's opposite to the direction of the force exerted by Griffiths, but in the
See this negative, there will be induced negative and positive charge.
yes, sir.
This negative charge will be pulled by the positive charge. This positive charge will be pulled by the negative charge. Vertical components cancel out. Horizontal components will be pulling it in.
Understood, sir. I got my understood, sir.
Note. Energy stored in the fringing fields themselves stay constant. Energy stored in the fringing fields themselves stay constant as the slab moves. Energy stored in the fringing fields themselves stay constant as the slab moves. As the slab moves. what does change is the energy well inside the capacitor. What does change is the energy well inside the capacitor. Where the field is nice and uniform. Where the field is nice and uniform. Now you know which force was the root cause for the liquid level to rise?
Yes, sir.
Fringing field. Why HCV went wrong? Because he has taken the force only on the upper surface of the liquid. Right? And he equated it to mg. थोड़ा ध्यान से सुनिए. What HCV did here was he took the force on the upper surface of the liquid and he equated it to mg. Hence, he went wrong in his last solved example. Till here, is it clear?
Yes, sir.
Now, there are some people who yet believe that HCV is right. What is their argument? They say, force on one side of the liquid, आप लोगों ने भी लिया है. In surface tension. Surface tension is done.
Yes, sir.
Yes, sir.
Yes, sir.
Now you took this force, this is theta, this is cos theta, and you equated it to mg. You did this in surface tension. तो गलती क्या है भाई साहब? HCV ने भी वही तो किया है. Problem is here there were no fringing fields. There was no normal force underneath. Here you have a normal force. You have force on the other side in the downward direction. And above all, you have got fringing fields. You are missing out on quite a few forces. You didn't take the normal force. You didn't take force on the other side of the liquid. Here on the other side of the liquid, there was no force. So there were the only two forces which you accounted for. And if you people have observed carefully, in this case, even if you take potential energy and derive, you will get the same expression. Yes or no?
Yes.
Surface tension mein you have calculated this using potential energy, you get the same height for the capillary. Right? That means there is no other force acting on it. Here there are quite a few other forces acting on it which you have missed out when you are taking force on one side of the dielectric. Hence, the current edition of Iridov, the answer given is correct. And there is another question designed by Iridov on the same concept. What he did is a circular plate rotating. 1 second, wait. I'll put this question. I wish I could put this diagram. This is one plate, circular, semicircular plate. There is another semicircular plate as well behind this board. And there is a dielectric There are two plates, semicircle, and a dielectric in between which is rotated. The dielectric is rotated this way. This angle is taken as phi. This is epsilon r. Radius is r. Find the torque to be applied to keep the dielectric in the position shown. Find torque to be applied to keep the dielectric in the position shown. To keep the dielectric in the position shown. Right? The two plates have a separation of d. The two plates have a separation of d. The two plates have a separation of d. So the thickness of the dielectric is also d. Thickness of the dielectric is also d. Right? It is hinged about the point O. And the plates are connected to a battery of potential V. Plates, above plate and lower plate, are connected to a battery of potential V. Two semicircular plates. The dielectric hinged at the center, and the dielectric is partly rotated out of the plates. Are you able to visualize the problem?
Yes, sir. Yes,
These
sir.
are the two semicircular plates, and the dielectric comes partly out. I need a CD to explain this, and I don't have one. I think I have. Listen. Yeah. Listen. These are the two semicircular discs. These are the two semicircular discs. Right? The distance between them is d. There is a dielectric in between, which is pulled out. There is a dielectric in between, which is pulled out by an angle of phi. What is the torque you have to apply to keep it in that position? Suppose you don't apply a torque, the dielectric will go inwards. Why? Fringing fields we just now did. If you don't apply a torque, the dielectric will be pulled inwards. Yes or no?
Yes, sir.
Fringing fields which we just now did. So he is asking you what is the torque you have to apply. So technically, I will call this C1 and this as C2. C is equal to C1 plus C2. C is equal to C1 plus C2. I'll be able to calculate this area, you'll be able to calculate C. Torque is equal to minus du by d phi. Technically, you told me F is equal to minus du by dx. No, yeah. I just made a change. Torque is equal to minus du by d phi. Calculate, it's connected to a battery. So your job becomes much easy. D by d phi of half CV square. So this will be minus half V square dc by d phi. Calculate dc by d phi and substitute, you get the answer. Potential is constant.
Done.
No, sir, just a second. So copied, sir. So will you solve this question?
क्या सॉल्व ही तो किया है मैंने क्या किया है मैंने
So how will you find the capacitance here, sir, in terms of theta? I'm struggling, sir.
You are asking me how to calculate the area if phi is given. If this is pi minus phi, you are asking me how to calculate this area.
So we take just that area for the capacitance and then we add in
So
parallel.
C1 and C2, you will know this area.
Yes, sir. Yes, sir.
C is C1 plus C2.
Okay, that way. Okay, sir. I got confused. That's why I was asking, sir. I understood my mistake.
Now, what kind of questions has HCV given on this? He has connected this to a battery, and this is capital N. You know the value of this force. This is B. This is connected to a battery. This force is epsilon naught B square by 2D into epsilon R minus 1. Equate it to mg. As simple as it. In some situations, to make it a bit more complicated, they dip this in a liquid. You'll have one buoyancy force in the upward direction along with it. No big deal.
Yes, sir. Sir,
Yeah,
we are left with cylindrical capacitors, right?
yeah. And spherical.
Because I told to complete HCA in last part, those questions were there.
Now, cylindrical capacitors. Ideally, just as you have taken infinite large parallel plates, you will take infinite large cylindrical. This is of inner radius R, this is of outer radius capital R. Right? Just as you have taken infinite large plates, you have taken infinite large cylindrical plates. Positive, and you have negative on this side. Negative on this side. Technically, capacitance is Q by delta V. Q by integral E dot dr. Obviously, with a negative sign, I'll substitute that separate. Delta V is minus integral E dot dr. V of the inner radius minus V of the outer radius is minus of 0 to small r to capital R E dot dr. Why are you taking potential of the inner minus outer? Because the outer is at zero potential. You have grounded the outer one. So the inner cylinder will be of greater potential, outer cylinder will be of lower potential. Is it clear till here? Potential of the outer cylinder will be zero because you have grounded it.
So only outer part of outer will be zero, right?
इतना emphasize करके मैंने बोला वही गलती कर रहे हो आप यहाँ पर ग्राउंड करो यहाँ पर ग्राउंड करो यहाँ पर ग्राउंड करो
अरे सर,
कहीं पर भी ग्राउंड करो potential of this body will be zero. Yes or no?
yes sir.
So now you are grounding the outer cylinder, so potential of the outer cylinder is zero. Now if you can tell me the field, my job is done. How will I tell you the field? I will assume a Gaussian surface. Gaussian cylindrical surface at a distance of small r. Integral E dot ds is equal to Q by epsilon naught, lambda L by epsilon naught. You are taking the length of the cylinder to be L. क्या यार length infinite अभी अभी बोला फिर L ले रहे हो. Parallel plate capacitance may be epsilon naught E by D. You have assumed infinite large plate, but area is taken. That means the plates are very close. Same happens here. E integral ds cos 0 is equal to lambda L by epsilon naught. Integral ds, this is curved surface area, 2 pi RL is lambda L by epsilon naught. E is equal to 2k lambda by R. Substituting this field here, will I get 2k lambda by R dr from small r to capital R? Will you be able to do this integration?
Yes
Take
sir.
this as R naught, take this as R naught, so that you know the difference. Small r is a variable, R naught is a constant. This potential difference, if you substitute here, this is lambda L by delta. Will I get the capacitance?
Yes sir.
How much is this potential difference? 2k
Minus 2k.
lambda ln of R naught by R.
Yes.
Capital R by R naught, no yaar, no R naught by R. Lambda L by delta V. 2k lambda ln of R naught by R. Lambda lambda will go, right? Two k lambda ln of R naught by R. Running short of space. Substitute that here, you get the answer. If you take it to the numerator, please make sure that you write ln of capital R by R.
Sir,
Hmm.
I had a conceptual doubt in just a parallel plate capacitor that like outer plates were initially given some charge, two different charges.
Outer plate or outer plate?
Outer.
Outer surface.
Yes sir.
How much?
So just a second. So there were three such plates.
Hmm.
So one first plate has total Q on it. Second has 2Q. And so now we have told to find current if the outermost two are connected with a wire. So current in the wire, charge in the wire we are asked to find.
You know the initial charge, this is Q and this is 0.
Yes sir.
So find the charge distribution, 2Q plus this will be 3Q by 2, 3Q by 2. This will be Q by 2
Minus Q.
minus Q by 2, Q by 2, 3Q by 2 minus 3Q by 2.
Yes.
Sorry, this I did when the switch is open. This is when the switch is open. Now when the switch is closed, can you find out the new charge?
So why will it change?
ये problem किया भी है class में. You took x here. The last problem of Gauss law. Y here minus y. If this is 2q plus y minus of 2q plus y and z. किया है कि नहीं?
Yes, sir, understood.
Now I know the new final charge, I know the initial charge. When you are connecting these both, you are bringing these both down to the same potential. So there will be charge flowing. We have done this in the class. You have it in your class notes.
Understood.
Substitute the value for K as well. Don't leave it in K. That will be the capacitance of the cylindrical capacitor.
Done, sir.
Spherical capacitor. This is small r, this is capital R. This is Q, this is minus Q, this will be 0. We already have done this charge distribution, right? C will be Q by delta V. Q by delta V. I know the here. Technically, I should apply Gauss law, find out the field, then find out integral E dot dr. Here, directly I know delta V. How do you know that? V small r is KQ by small r, K minus Q by capital R. V capital R, KQ by capital R, K minus Q by capital R. We dealt with this in Van de Graaff generator. Right? V small r minus V capital R is KQ into 1 by R minus 1 by capital R. KQ into 1 by R minus 1 by capital R. This will be 4 pi epsilon naught 1 by R minus 1 by capital R. C is equal to 4 pi epsilon naught 1 by R minus 1 by capital R. If capital R tends to infinity, why should it tend to infinity? That means I have only one sphere. Capacitance will be 4 pi epsilon naught smaller. If there is only one sphere, its capacity is 4 pi epsilon naught smaller.
Done, sir.
Here remember, there is another way of calculating the capacitance as well. If you have two spheres this way, small r and capital R, energy stored is q square by 2c, rather small q whole square by 2c. This is the general formula of the capacitance. You know this is q, this is minus q and 0. Do you know the total energy stored in the system, self energy of this? Q square by 8 pi epsilon naught small r. Self energy of this. Q square by 8 pi epsilon naught capital R. Interacting potential energy between the two. 1 by 4 pi epsilon naught Q minus Q by capital R into plus. Because of this, the potential is 1 by 4 pi epsilon naught minus Q by capital R. That into Q. This is the net total potential energy equated to Q square by QC, and find out C from this. Verify if you are getting the same answer or not.
Excuse me, sir.
Hmm.
So shouldn't the energy of a capacitor be in addition to the self energy of the capacitor rather than being equal to it?
Why should it be addition?
Sir, because the self energy, as you said, sir, self energy is by the virtue of it having some charge, and then we charge a capacitor further to bring it up to a particular Q.
Finally, after calculating self energy, did we calculate the net total energy half epsilon naught E square and show you that there is energy stored?
No, sir.
When we calculated self energy होने के बाद, self energy calculate करने के बाद, total energy stored in the system, did we take half epsilon naught E square into volume?
Oh, yes,
and
sir.
integrate and show to you that it is equal to the self energy?
Yes, sir.
So why that doubt now? Total energy stored, even energy of a capacitance you calculated from that only, half epsilon naught E square.
Yes, sir. Understood, sir.
if I have got two capacitors this way, I'm having a boundary of dielectric. This is small r, this is capital R. This is epsilon R1, epsilon R2 and ground. Now this is as good as two parallel plate capacitors with a dielectric epsilon R1, epsilon R2. Right? Call this as X. I'll call this C1, I'll call this C2. 1 by C equivalent is 1 by C1 plus 1 by C2. C1 will be epsilon R1. What was the formula we derived for this? 4 pi epsilon R1 epsilon naught 1 by R minus 1 by X. C2 4 pi epsilon R2 epsilon naught 1 by capital R minus 1 by X. From small r to X is one capacitor, from X to capital R is one capacitor. I think I did the reverse here, 1 by X minus 1 by X. So C1 and C2 are in series. And once they're in series, you know the equivalent capacitance.
Done, sir.
Some situations of spherical capacitors, they will give you some hypothetical problems like this. They'll give you two spheres. This is of radius R1, this is of radius R2, this is Q1 and this is Q2. The distance between them is D. Very orthodoxly, capacitance, how do you calculate? Take Q and minus Q divided by delta V. How do I find delta V? Minus integral E dot dr. Find out field somewhere here, integrate it from here till here. But you can altogether avoid that by equating Q square by 2C. 2 self energy of this Q square by 8 pi epsilon naught R1 minus Q whole square by 8 pi epsilon naught R2 K Q minus Q by D K 1 by 4 pi epsilon naught. Right? You should get C as 4 pi epsilon naught 1 by R1 plus 1 by R2 minus 2 by D. A hypothetical problem created just for the sake of a problem.
Done, sir.
The same situation is given as a problem in Eroviva for cylindrical capacitors. What he did is he took two thin, infinite long wires. Two thin, infinite long wires. The radius is smaller for both of them. Distance between the centers is taken as d. I'll take lambda minus lambda. Q and minus Q ले रहे थे ना यार, अभी तक lambda क्यों कर लिया आपने? Infinite long wires. No. C is lambda L by delta V. How do you want me to get delta V? Minus integral E dot dr. And what is the value of integral E dot dr? 2k lambda by r. 2 will go because of each wire, the field at a distance of r, or call it x. You have already taken r. Call it x. Call it dx. Why will you take k lambda by x here? Because of this, it will be 2k lambda by x. Because of the negative charge, 2k lambda by x. K lambda by x into dx. You are going from x equal to r to d minus r. Total distance between the centers is d. I want up to the surface. This delta V. Substitute here, you get the capacitance of this capacitor. Two infinite long cylindrical wires. Two infinite long cylindrical wires.
Sir, shouldn't it be 4K lambda by?
Yes, sir.
My bad. When we are adding both 2 plus 2, I'm not concentrating today.
Done, sir.
This completes capacitance here. I was very keen on completing this chapter for you people. Right. Now, when is our next lecture?
Next week.
This week, Saturday, we don't have a lecture.
No, sir.
Did I send you the capacitors assignment?
Yes, sir.
HCV, capacitors, assignment, booklet. Doubts to be taken, right? What all have you people completed?
HCV.
Today evening, can we keep one half an hour or 1 hour of a doubt lecture and finish at CV? Today, tomorrow, day after, may any one day. Your choice.
Sir, tomorrow.
So tomorrow,
Tomorrow, what time?
so tomorrow we don't have lectures, so whatever time suits you.
9 o'clock?
Okay, sir.
Right.
के घर में किसी के घर में गणपति आ रहा है 9 o'clock not possible. Sunday I have classes here. Sunday not possible. Tomorrow time बताओ. One student type keep it in the evening. I am okay anytime.
I can keep it in like 4 o'clock in the afternoon. That would be fine.
Is 4 okay with all?
Yes, sir.
Yes, sir.
Yes, 4 p.m. I'll send the link. I'll take up the doubts tomorrow evening 4 o'clock. If possible, try to finish the assignment as well. दोनों खत्म कर.
So
Is
4
it clear?
to for how many hours?
कितना आपको कितना डाउट्स है उस पर है. HCV तो खत्म कर दूंगा. अगर जल्दी खत्म हो गया तो कैपेसिटर भी 1.5 आवर तो ले लूंगा.
Okay, sir.
कैपेसिटर का असाइनमेंट भी कर लो ताकि कंप्लीट कर लूंगा. बुकलेट चाहिए तो नेक्स्ट वीक रख सकता हूँ.
Assignment before the booklet?
या असाइनमेंट बिफोर द बुक.
Okay, sir.
ओके.
So next week you'll keep any class as doubt lecture?
We'll keep one like this. Just as tomorrow evening 4 o'clock we kept. Regular class we will not convert into a doubt lecture. Regular class will go ahead with current elements.
Okay, sir.
Evening 4 o'clock we'll keep and we'll keep finishing of the doubts. Is it clear?
Yes, sir.
Yes, sir.
Today, though I know I have some more time, but I'll stop here. I'll continue tomorrow evening 4 o'clock.
Thank you, sir.
See you people in tomorrow's class. So tomorrow itself we'll wish you happy Ganapati Chaturthi.